we're going to pick up where we left off in class, and that's with number 3 on the worksheet. So I've got it copied here. This one has a denominator that's already factored, and we can identify both of those factors in the denominator as linear factors. X minus 1 is linear. X plus 3 is linear. It happens to have multiplicity 2. So we will deal with that in our template. In the template, that means we need to break this down into a sum containing an a over x minus 1. Okay, linear denominator gets a constant numerator, plus I need an x plus 3 to the power 1, and then an x plus 3 to the power 2 as denominators, because those all could have been part of the original sum that gets me to that answer. Numerators, so x plus 3 is linear, so it gets a constant, letter B. X plus 3 is also linear. If you can cover up the degree and you're still left with the linear factor, you know it's linear, so this one gets a C. What I need to do next is to compare my numerators. So I'm going to use the same shortcut that we used in class. My denominator is right here, so I'm going to go ahead and just multiply in what's missing. The a over x minus 1 is missing the x plus 3 quantity squared. The b is missing an x minus 1. And it's got one factor of x plus 3. It needs one more to get the power 2. And then finally, the c has the x plus 3 in its denominator, but it needs the x minus 1. This is the numerator from the template. This needs to equal the numerator in the original rational expression. So there it is. Zeroing or using zeros or zeroing this out is the easiest way to start if you can find some, and we've got some. I know that I can zero out with some negative 3's there and there. That would clear out the a and the b for me. I can also clear out some values with a positive 1. So a positive 1 there and there will clear out the b and the c. Let's go ahead and start with negative 3. So when x equals negative 3, I'd lose the a times 0. b is multiplied by a 0 as well. So I get c times negative 3 minus 1. On the other side, I get 3 times 9 plus 17 times negative 3 plus 12. So if I run that into my calculator, I get negative 12 on this side, and c times negative 4, so negative 4c on that side. Then that tells me that c is equal to 3. So there's one of my values. I can also, that was with the 3, I can also use the 1. So let's go back up, do it over again with a 1. Okay, so I keep the a this time. So a, that would be 1 plus 4 squared. The b is eliminated, and so is the c, because I get zeros. On the other side, with the 1, I get 3 plus 17 plus 12. I jumped the gun here. 1 plus 3 is what I should have, and that would give me 4. So 1 plus 3 would be a times 4 squared, so that's 16a, glad I caught that error, equals 32. When I do the division, 32 divided by 16 is 2, so a equals 2. I wish I had one more 0, but I don't. I have one more letter. I have the a and the c done. So for my original template up here, I've got the a and the c done, but the b, notice it's got both factors in it, so I can't finish this off by using those zeros. So I need to go to the second plan, which is to use coefficients. I don't start with coefficients unless I have to, and I'll show you one of those, but I only use it when I have to. What I really need to solve for is not everything, it's just the b, and I see that the b, I'm not going to multiply it all the way through, but the b will have an x squared term in it. The b will also have a constant and an x term, but an x squared, if I compare the x squared coefficients, that will get me there. So let's go ahead and start by moving through the template expression. I'm going to have an x squared here. I'm not going to multiply it out, but I know I get an x squared here multiplied by the a. So there's one x squared term. I'm going to get an x squared here multiplied by the b. So I get a bx squared. I do not get an x squared here. The x squareds on this side need to equal the x squareds on the other side. So they need to equal 3x squared. Coefficients need to be the same. So a plus b needs to equal 3. We know what a is, though. A is 2. 2 plus b needs to equal 3. And that tells me that b is equal to 1. That was my last value left to go. So I've got my answer now. That partial fraction decomposition is starting with a 2 for a over x minus 1. B we got last, that's 1 over x plus 3. And then finally C, 3, which is x plus 3 quantity squared. So there's my answer. I've got some more examples to work through with you. Let me go to this one next. It's just a nice, really simple one. One really similar to what we did in class. So we'll just call this example. And this is a 2x plus 1 divided by x squared plus x minus 2. I do need to factor that denominator so I can figure out what my template's going to look like. So it factors as x plus 2, x minus 1, both linear factors. In the denominator, no multiplicities, so I can go ahead and jump right into my template. I need an x plus 2 in the denominator and an x minus 1 in the denominator. This is how I would get two fractions that would add back up to my original rational expression. These are linear. I want proper fractions, remember, so I need those numerators to be constants, 1 degree or less, so that would be a and a b. And this needs to equal my original fraction, plus 2, and I'm going to use my shortcut though. What I really need to compare are my numerators. So getting a common denominator here, using the common denominator I was given, a has the x plus 2, but it's missing the x minus 1. So a needs the x minus 1. B's fraction has the x minus 1, but it's missing, so I multiply in the x plus 2, and that needs to equal the original numerator. I'm going to go ahead and use zeros. Again, whenever I can, I start by using zeros in quotations. So I use my zeros. A 1 will zero the a out, and a negative 2 will zero the b out. So x equals 1 is where I'm going to start. That's going to eliminate the a for me. When I put a 1 in, I get 1 plus 2. On the other side, I get 2 times 1 plus 1. So 3b is equal to 3. Nice. And b is equal to 1. Okay, there's my first value. I need a as well. Negative 2 should find it for me. Negative 2 is going to zero the b out, but it leaves me with the a. Negative 2 minus 1 on this side. On the other side, that's 0. So on the other side, I get 2 times negative 2 plus 1. So negative 3a is equal to negative 4 plus 1, negative 3. Really nice. And a is also equal to 1. Our answer then, I've got both numerators, so 1 over the x plus 2 and 1 over the x minus 1. Okay, really, really a nice problem. Let's take a look at this next one. Sometimes you can use the zeros for part or all of your values. Sometimes you can't, and this is an example of that. In the numerator, we've got 2x cubed plus 7x plus 5 divided by x squared plus x plus 2, quantity x squared plus 1. Gosh, I can try and factor this one. I need a 1 and a 2 here. I would never get to a 1 as the coefficient on the x. So what I've got left here are two irreducible quadratic factors. They can't be factored further. Those go into my template. So when I put my template together, I need an x squared plus x plus 2 in a denominator and an x squared plus 1 in the other denominator. These are degree 2. So I need one less degree in the numerator, which would be degree 1 or linear. I think of those as mx plus b for a linear equation, but I'm on a, so this is ax plus b. That puts me at cx plus d. So I've got these. I'm going to go ahead and get my numerators by getting the correct denominators. So the first fraction has the x squared plus x plus 2, but it's missing that x squared plus 1. So ax plus b. its fraction is missing x squared plus 1. The cx plus d fraction has the x squared plus 1. It's missing the other denominator factor, and that's x squared plus x plus 2. And I know that this all needs to be equal to, put an arrow there, 2x cubed plus 7x plus 5. Remember I said these guys are irreducible? That means there is not a real number, I should say not an integer, so there's not an integer that will zero these out. So I'm stuck. I can't use zeros. I would love to. That is always my first choice, but I can't. So instead, I need to use coefficients. I start with the highest degree I've got, and that's cube. So I go ahead and start with x cubed. This is when I'm starting from the coefficients. So x cubed. I'm not going to multiply all this out. I'm just going to look for x cubes. If I were to multiply it out, I can get an x cubed here. That would be an ax cubed. There's no other way to get an x cubed in this FOIL. If I were to multiply this out, I can get an x cubed here. So that would be plus cx cubed. There's no other way. On the other side, we've got 2x cubed. That gives me a coefficients only plus c equals 2. We're going to call that relationship 1. X squared is next. Okay, so to get x squared, I'm looking for x squared. I can't get it from the ax, but I can from the b. So that would be bx squared. No other way there. I move on to here, cx times x. So I can get a cx squared and a dx squared there as well, plus dx squared equals, there are no x squareds here, so that would be 0. Coefficients only are b plus c plus d equals 0. We'll call that relationship 2. Now for the x's, I can get one here, ax times 1, so that would be a times x. Not from the b. cx times 2, so plus 2cx. And d times x, I can get that one as well, equals, there are 7 of those, 7 x's. If I drop my x's, I have a plus 2c plus d equals 7. I've got one more relationship to go because I haven't done my constants yet. Okay, constants. Ax is never going to give me a constant, but b will, so b times 1. Cx won't, but d will, 2 times d. Did I get them all? And then that's going to equal a 5. And so I'm just going to move this over. It's already done because there are no variables, only coefficients. But I'm going to write that down as relationship number 4. This is my system of equations. I'm going to work through this and try and eliminate variables so that I can start solving for some. I'm going to go ahead and start with that relationship number 1. And I'm just going to rewrite it and say a can be replaced with a 2 minus c. So I go through and I look for an a. Here's one. I can replace that with a 2 minus c. So in equation 3, so I'm using this relationship, I've got 2 minus c, right? 2 minus c, there's my a, plus 2c plus d equals 7. If I simplify that, the 2 comes over, gives me a 5. 2c minus c gives me 1c plus d equals 5. This gives me another relationship I can use to do my substituting. This I can move the d over and I can say c is the same as 5 minus d. And I'll be done with that relationship. Okay, c is the same as 5 minus d. I would really like to get somewhere. So if I replace it in, well, let's just do c. Let's just do this one. I haven't done equation 2 yet. B plus c, which is 5 minus d, just about there, plus, oh yeah, perfect, 5 minus d, that was c, right, plus d equals 0. The d's end up canceling. So b plus 5 equals 0. B equals negative 5. Yay! I get so excited when I find my first value because now things really start to come together. So if I know that b is equal to 5, I can start to put things back in. Let's go to number 4 here. If I know what b is, I can figure out what d is. So if I go to relationship 4, I know what b is. So b is negative 5 plus 2d equals 5. So this tells me 2d is equal to 10. There's my second one. D is equal to 5. I've got 2 left to go. But remember this relationship right here? I can get C really easily. C equals 5 minus D. So C equals 5 minus 5. C equals 0. So once you find that first one, you're good. And then where was that A relationship? There's that A relationship. So if I go back up to that A1, A was 2 minus C, but we know that C is 0, so A is 2. Okay, a really tedious method to go through, but once you start to find a value, it's not bad, but it's a little bit messy. Okay, what is my answer? I found all of my values. I'm going to put those back into my original, where is it? Right here. I'm going to peek here. A is 2. So I've got x squared plus x plus 2, and that's 2x. B was negative 5 minus 5 plus C. C is 0, so I don't need an x. This is over x squared plus 1. But D, where was D? D is 5, equals 5. Okay, so that is number 2. And I'm checking my answer here, and it looks great. Okay, let's do another one. That's a coefficients only. Those are messy. There's not going to be a lot of them, but sometimes you need to do coefficients only. Let's do, I don't think we did one like this yet, did we? Let me look back up. Yeah, let's do this one next. So here's another example. Let's try to get a nice variety in. This example has 3x squared minus x plus 2 in the numerator, x plus 1, x squared plus 5 in the denominator. This would be a great place for you to hit pause and see if you can set up the template on your own. See if your template matches mine. So hit pause, and then when you're ready, hit play again and see if your template matches mine. Okay, linear, quadratic. I'm going to go ahead and write the template, so hopefully I already hit pause. X plus 1 is linear, so I get an A there. X squared plus 5 is quadratic, so I need a linear in my numerator, A, bx plus c. Okay, how'd you do? Let's get those numerators with that common denominator. A is missing x squared plus 5. Bx plus c is missing x plus 1. And I need this to equal my original numerator, plus 2. I can zero just one thing out, and I'm going to do it because it's going to simplify my life. Use a 0, and that's with negative 1. Okay, so this is going to give me A times 1 plus 5. That all zeroes out, and on the other side I get 3 times 1 minus negative 1 plus 2. Okay, 6A equals 3 plus 1 plus 2, that's 6. Okay, nice. A is equal to 1. Next, write 1 down, 2 to go. I can't zero anything else out because of that quadratic. There's no other integers I can pick on. So next, let's use coefficients. I've got A, I need B and C. So B is attached to an x squared, so that'll find a B for me. Let's just start with x squared, finding all the x squareds on the left. There's an ax squared, there's going to be a bx squared. C won't give me an x squared, that needs to equal 3x squared. So this tells me A plus B equals 3, but I know that A is 1. So that means B is equal to 2. Okay, just one left to go. I need to get C. I can get C with either my x's or my constants. Let's do the x's. I don't think it matters. No x's here in the A term. I've got a bx, so bx plus a cx. On the other side, I have a negative x. Okay, coefficients only. b plus c equals -1, but b is 2, so c is -3. I'm going to go back up to my template, and I'm going to put those values in. So, give myself a little more room here. My answer is a, which is 1, over x plus 1, plus bx plus c, 2x minus 3, over x squared plus 5. How'd you do? Okay, let's do a couple more. I've got one actually that would be way too challenging to do, but it's a really great one just to practice that template. And it's this one. So this is setup only. 7x squared minus 30x plus 29 divided by x minus 2 squared, x minus 3. Okay, again, it'd be great if you paused it for a minute, see if you can get the correct setup, and then hit play, and make sure you can match mine. Okay, are you back? So this is x minus 2. This is linear. I want to see if you got this one right. Linear, I've got a degree 2, but I can cover it up, so it's linear with multiplicity 2. This one is linear. So when I set this up, I need some room, I need to count up to my power. So an x minus 2 could be an addend. An x minus 2 squared, oops, minus 2, that says x minus 2 squared could be an addend. And an x minus 3, all linear denominators, so I need all constant numerators. Okay, so there's one setup only. Let's do another setup only. Make this one really challenging. Okay, so for this one, I'm just going to make up stuff. This would probably be really ugly if you tried to do this for real. Let's do x cubed, and then x squared plus 1 squared, and then x minus 3. Okay, again, pause and see if you can come up with the correct setup. That's the key. I mean, the rest is tedious algebra, but if you don't have it set up correctly, you're never going to get there. Decide which are linear, with multiplicities possibly, and which are quadratic. Okay, so here's what I did. X actually is linear. This one's tricky, but I can put my finger over the 3, and I can see my linear factor. So this is linear with multiplicity 3. X squared plus 1, I can cover the 2 up, but I'm still left with the quadratic. So this one's quadratic with multiplicity 2. And this one's just a good old linear one. Okay, I'm going to put my template here. I need to count up to my multiplicities. X cubed means I've got an x, an x squared, and an x cubed. For that quadratic, I've got an x squared plus 1, and an x squared plus 1 squared. And then the last linear is an x minus 3. Okay, linear factors. These are all linear. I can cover that up. Linear base, degree 2, linear base, degree 3. So these are all linear. They all need constants. A, linear with multiplicity, so B. Linear with multiplicity, so we need C. X squared plus 1 is quadratic, so I need a linear numerator, mx plus b, a, b, c, that'd be a dx plus e. X squared plus 1 squared. We ignore the multiplicity, it's quadratic, so this would be f, x, e, f, g, plus g. This one's linear, so it just needs a constant numerator. And that's all I've got. I hope this helps.